Hello, everybody. So, welcome to yet again another edition with Special Maths Academy. So, today we'll be looking at solutions to the corner for the month of February 2021. Okay, so we'll be looking at number theory. Yeah, so we asked to prove or disprove if A, B, and C are positive coprime pairwise coprime odd integers. Then there exists a unique, so there exists a unique positive integers x, y, and z such that we have all four conditions. Okay, so let's get into it immediately. So what we're going to do is we are going to prove. So this is actually true, and we're going to see why. So we're going to get proof. All right. So from the first condition, we have that since A is a GCD, so at least A is a divisor of each of these numbers. And devise this. Okay. And also we have in a way that B divides, that's from the second one. We have that B divides 2y, B divides 2z, and B divides 2x plus 1. And finally, from the other one, we have C divides 2z minus 1, C divides 2x, and C divides 2y plus 1. All right, so one of such is that we could look at this, it's kind of asymmetric, but if we consider the sum of the numbers we have here, we see that A divides 2 into x plus 1 plus z. And the same goes here as well. So B divides this number as well, and C divides this number as well. So long as 1, 2, and 3 are satisfied, then we have this. Now, A, B are all odd numbers, and in fact, they are also coprime. So this ultimately implies that A, B, C, which is the LCM, divides this number. Okay, so this is a very key detail. All right, then moving on. If we focus now on a single variable, let's say x, we have that A divides 2x minus 1, B divides 2x plus 1, and C divides 2x. So in terms of modular arithmetic, this is just a system of congruencies. So mod A, 2x is congruent to minus 1, mod B, and 2x is congruent to 0, mod C. And by Chinese remainder theorem, this has, since A, B, and C are odd, so they are coprime with this. Coprime. So it means this has a solution, and by Chinese remainder theorem, there's a unique solution x naught, such that x naught lies between 0 and the product. They are all pairwise coprime, and x is congruent this mod. We have this form where x is a unique integer. So we don't have, first for this, a solution to this in this range, and also we don't have multiple of those, so just have a unique one. So we'll call that x. Okay. All right, so so what this gives us is that we can write x as x naught plus let's say k times abc sum k z. All right, now we're also interested in x being positive right here. So we just make use of that. So since x is greater than 0, this implies that x naught plus kabc is greater than this. So kabc is greater than minus x naught, which is greater than minus abc. So k is greater than minus 1, meaning k is at least 0. Okay. And then one more thing, we have that x naught cannot actually be 0 because that would contradict this value here, 2x being congruent to 1. So x naught cannot be 0. So I'm going to change that inequality to a stricter one. So this is 0 strictly less than x. Okay. So it's an important bit. And this is some other important bit. All right. Now, in a very similar way, we can get results for y and z. So similarly, we have that there exists unique y naught between 0 and abc, and also z naught in the same range, such that such that y is equal to y naught plus let's say l bc, and z is z naught plus, so this is some l elements, l and m elements of z greater than or equal to 0. Okay, so this is what we have. Now we're going to combine that with what we have here. So let's call that star. Okay, so but star implies AC divides x plus this. So by plugging in all these expressions we have, we get I divides k plus l plus m abc. So this means that abc must divide the sum of these numbers, and now given the range of x naught, y naught, and z naught, so we have that this sum actually lies strictly between this and 3 abc. Yet it's a multiple of abc, so it means that there are only two possibilities. So this is either equal to abc or 2 abc. Okay. So first of all, we're going to show uniqueness, because I want to show there exists a unique positive integer satisfying all this. So we're going to show uniqueness. So if we have any x, y, z satisfying all 4 of these conditions. Then from the first 3 conditions, we have all we have so far. And then for the last condition, what that boils down to is the last condition, we have that ABC is greater than or equal to maximum of X, Y, Z. So this implies, first of all, that ABC is greater than or equal to X. It's also greater than or equal to Y and greater than or equal to Z. Now, by plugging in the expressions for X and Y, X, Y, and Z, so this, for X, for example, this means we have this K, ABC, which is bigger than KABC. So this means that K is less than 1, but we already had this greater than 0, so K has to be 0. Similarly, we also have L is equal to 0 and M is equal to 0. So this means for what any such XYZ that satisfies this, then we do need X to be exactly X naught, Y to be exactly Y naught, and Z to be exactly Z naught. Okay. And this itself is unique. So we can't have 2 values. So this is very specific. So XYZ particularly will have to be X naught, Y naught, Z naught. And for each of these, they indeed satisfy this condition because we are all less than ABC. So maximum will be less than ABC. So we've shown uniqueness. What we want to show now is that we want to show existence, meaning that this particular choice. So if we have any XYZ that works, it must be this triple. But then that doesn't mean this triple is going to satisfy all the conditions. And that's because what we've used so far is just reduced from the first one that will have this divisibility, but that doesn't make sure that A will be the GCD. Okay, so we're just going to show that GCD is actually for the first one. So we want to get GCD. So let's say the GCD of 2x minus 1, 2y, and 2z plus 1. Yeah, okay, is equal to, let's say, capital A. We want to show that the capital A is equal to small a. So what we get here is that since A divides 2x naught, sorry, let's put this as x naught. So we know this happens from the solution of the system of congruencies. We also know this happens, and we also know this. So that means it divides their GCD, which is equal to A. So that means A is equal to a multiple of, let me just write it as A divides A. So we have this. Okay. Now we have all we had before. We can still do the same stuff with capital A, because capital A is also a divisor of all these numbers. So we get capital A divides this this. And since we also already had all these counterparts, we already had all this from the definition of these numbers, and C to C naught to X naught and to Y naught plus 1. So we already had all this. So this is just like going through what we had before all over again. The only thing we just need to make sure is that A is odd, which is true because of divides an odd number. Also, that A and B are coprime. And that is true because A divides this number, or we could use something better. Let's use Y naught. So A divides this and B divides this. So suppose they had a common divisor, D, then D will divide A and B, meaning D divides 2Y naught and B divides 2Y naught minus 1. So D has to divide 1, meaning that every common divisor can only be 1. Okay, so indeed they are coprime. The same argument works for A and C. So we have exactly the same setup as we had before. Only difference is replacing capital A by small a. Okay, so meaning at the end of the day that we must have that there exists by Chinese remainder theorem once again. So it means that x okay, so what this means is not really Chinese remainder theorem yet. So just similar trick to what we did before. So one part we're still missing is to take the sum, which is 2x naught, y naught, z naught. Since a is odd, once again we have that a divides this, and since it's coprime with b and c, we've just shown, this means that the product will divide this number as well. So since we're working with positive numbers here, this is greater than or equal to a, b, c. All right. But on the other hand, we know that this is at most 2abc. So this means that 2a is greater than or equal to a. And we already had that a must divide this, and also capital A is odd. So this pair here means that a is capital A is small a times some odd t. So this is greater than or equal to 1. And plugging that here, see that you can only get this forces a to be equal to exactly a. Okay, so that means the GCD of this number, these numbers here, which we called capital A, is exactly the small a we wanted. So indeed the first one is satisfied, and in a similar way the other two will satisfy. Of course, we have the fourth one being satisfied as well. So indeed there exists a unique positive integers x, y, and z satisfying all this. All right, so thank you once again for being part of this. So hope to see you in the next problem.